So today we are going to discuss stochastic differential equation. So first let me describe what do we mean by a stochastic differential equation. Let capital T is positive, okay. So here we are describing only finite horizon stochastic differential equation that can later be generalized for close 0 to infinity, but for our discussions we are taking only a finite time interval. So let capital T is positive, and imagine that we have B and sigma given. B is called the drift coefficients, that is a function of T and the space variable. So here space variable is coming from n-dimensional Euclidean space, and B is the function of T and X and giving another n-dimensional vector. On the other hand, sigma is taking value T and space variable X and giving rise to a matrix, n cross M matrix, okay. And these two functions are assumed to be Borel measurable functions. We consider the stochastic differential equation. We call this equation as SDE for our repeated reference, that dxt is equal to b of t comma xt dt plus sigma of t xt dwt. Such equation should be understood that there are some integration sign involved. So you can see that x is the unknown here, which appears on the both sides of the equation, and that unknown, if you integrate that sigma of t of unknown, and with respect to Brownian motion, that integration 0 to t, and here also b of t xt dt is 0 to t if you do that unknown, and then what are you going to get is exactly xt minus x0. Okay, so that is the way one has to understand a stochastic differential equation. So this is true for all small t belongs to 0 to capital T. So here initial condition is x0 is equal to z. Here in this the w, as I have mentioned earlier, is a Brownian motion, m-dimensional Brownian motion here. Here sigma is a matrix n cross a matrix, and this w is m-dimensional Brownian motion. So in this integration, what we are going to get an n-dimensional vector. Okay, and here this Brownian motion is defined on a filtered probability space omega f ft, where t is belongs to 0 to capital T and p is the measure. So here for this, I mean if x is the unknown process. Now let us discuss that what do we mean by a solution of this equation. There are various different meaning. So we are going to first talk about here strong solution. We say that x is equal to xt belongs to 0 to capital T is a strong solution to the SD if the following properties hold. First thing is that x is ft adapted, the same ft. So in principle I am assuming that okay, this x is defined on that probability space what is given here. Okay, so as w is given to us on this probability space in the filtered probability space, so we are looking for x on this. Okay, so x is adapted to this filtration. Okay, and x0 is z. Okay, so this is small z, so typo, and integration 0 to t bis xs plus sigma ij. So ij is the ijth element of the matrix sigma, sigma square ij is xs, this ds. So this modulus stands for just the modulus. It is not the, because this bi, correct, is not the vector bi. Okay, so this modulus. So this is finite, okay, for all t belongs to 0 to capital T. And here as we have written I and j, I is running from 1 to n, j is running from 1 to m. Here this is a typo. Okay, so that is the condition we want here, and since it's random variable, we mean that this is finite almost surely with probability 1. Now we call this x as a strong solution if this is the main thing what we must get. Okay, so that xt is equal to x naught. So x is the unknown which satisfies this equation. Xt is equal to x naught plus integration 0 to t b of s xs ds plus integration 0 to t sigma s xs dws. So this is true for all t between 0 to capital T, and we would observe this is true with probability 1. We would see this as probability 1. So if we get such process X in this probability space omega f ft p, then we are going to say that okay, that process X is the strong solution of the given SD. Okay. Next, we state this theorem of existence and uniqueness of SD. Imagine that B and sigma, whatever given before, has some special property. Okay, under certain special properties of B and sigma, then only we can assure existence and uniqueness of the solution. I mean, this is very natural because even you do not have Brownian motion component, then you just get ODE. We know for ODE also, we cannot assure existence and uniqueness of solutions unless we put certain conditions on the coefficient. For example, that Lipschitz continuity of the coefficient B, okay, that is required for uniqueness, otherwise one does not get. So we here are listing down those conditions. So if B and sigma have at most linear growth, okay, that is for some constant C, mod of BTX. So this this is norm, actually Euclidean norm. This, I mean, although I am using just the mod sign, is Euclidean norm of this vector, and this norm of sigma t is so this mod stands for this following functional, that square root of summation ij sigma square ij. Okay, so BTX plus mod sigma tx is less than or equals to C times 1 plus mod x. Okay, so like B and sigma need not be a bounded function. Okay, it could be unbounded, but it would be dominated by one linear affine linear function. Okay, so when such function, you know, any function satisfies this type of conditions, we call them that they have at most linear growth condition. Okay, so B and sigma, they have at most linear growth condition. Now this Lipschitz continuity, we must have that, we must impose this type of conditions. So B and sigma are Lipschitz continuous functions in space variable, that means with respect to this x. Okay, so here we are writing, what does it mean? That means that for some d, okay, some positive d, okay, we can have such type of inequality, that mod of BTX minus BTY plus mod of sigma tx minus sigma ty. So this is less than or equal to capital D times mod of x minus y. So this implies that these are continuous in this variable. Not only this Lipschitz continuous, because D is fixed. Okay, D does not even depend on T. Okay, here also C does not depend on T. So this is called global Lipschitz condition. And Z, the random variable for initial condition, is assumed to be independent of the Brownian motion, and also assume that it has finite variance. Okay, expectation mod z square is finite, is in L2. Why are we doing that? Because we want to obtain solution in the L2 space. Okay, so the conclusion of this theorem is that the SD has a continuous solution X. Okay, in the following class, that X is adapted to. So here, I mean, I'm writing that sigma algebra generated by Z and also the filtration FT, because you know that when we talked about FT, we just talked about that okay, Brownian motion is adapted to FT. That does not mean that Z would also be, I mean, you know, measurable with respect to F0, say. So to mention that, we write down this, that okay, that sigma algebra generated by FT and Z both together. So in this occasion, it is also important to mention that often we start with just the filtration generated by the Brownian motion, the usual filtration, that the Brownian motion, okay, we take, and then for each t, okay, Wt, and we take the filtration generated by Wt. And then that may not satisfy the usual condition, as we have seen in the, I mean, towards the few of initial lectures, that we augment few more sets. We call those negligible sets. I mean, sets which are subsets of zero measure sets, so that we get a complete, so that the measure on those sigma algebras become complete, and also we take care so that it becomes right continuous. So all those things we do. I mean, most of the cases people start with just the filtration generated by the Brownian motion, but then augment with some more sets so that it satisfies the usual hypothesis. So for that, one says in a simple word that the usual filtration generated by the Brownian motion. Okay, so that is often obtained here. Okay, so we don't bother much because we are assuming that, okay, that is given to us. Okay, a filtered probability space is given to us and the Brownian motion is given to us, and then X is a process in the same filtered probability space, and then it satisfies that equation. Okay, it is also, it has continuous path, and it has this L2 norm finite. Okay, this is xt square integration 0 to capital T expectation. This is finite. So this is actually the L2 norm with respect to the product measure, the Lebesgue measure on 0 to t, and the probability measure on the omega. Okay, so the product measure of these two measures is taken here, and this is the L2 norm under L2 norm of x under that measure. Okay, so the proof starts here. For the proof, we need certain things. So I am just writing this is a trivial inequality. So when you have a, B, C vectors in Rn, then square, I mean, like, dot product. Okay, a plus b plus c square is less than or equal to a plus b so c whole square plus a minus b whole square plus a minus c whole square plus b minus c whole square. That you can see because these two terms are same, but we are adding some few more things. So this inequality is trivial. And then if we break these things, we would see that, okay, that is equal to 3 times a square plus b square plus c square. Clear? So we are going to use this inequality to break some terms in parts. So here we write down x superscript z1 and subscript t. Here x superscript, so the bar is typo, x superscript z2 subscript t. So what do they signify? So this signifies the solution of the SD where the initial random variable is z1. Here this is initial random variable is z2. Okay, solution of SD with z1 and z2 be the initial conditions respectively. Then we consider this L2 norm with respect to probability measure. So t is fixed here, correct? Expectation of xz z1 t minus xz2 t, okay, mod square. Okay, so that we consider. So that is less than or equal to, from the above inequality here, because here these two are this vector, correct? Okay, so this vector can be written as solution of the SD, and right hand side of the SD has 3 different terms. So here this also has 3 different terms, and then if we take the subtractions term by term wise, then there will be one term z1 minus z2 would appear here, then plus, then integration with respect to dt term, that difference would appear here. So which is like, bs x z1s minus bs x z2s, that term would appear in integration. And then there would be another terms that dw, the Brownian motion integration term would appear, where sigma s z1s minus sigma s z2s, this thing would appear. So here the difference would appear, here the difference would appear. So this difference would appear. So this is better to show. Okay. Okay. So those 3 terms would appear here, and then square is there. So a plus b plus c whole square is less than or equals to 3 times a square plus b square plus c square. That we are going to apply here. So it is less than or equals to 3 times of z1 minus z2 square. Like a would be my z1 minus z2. Okay, and then 3 times that, what is this s? S is b of x z1s minus bs x z2s. So this difference would appear here. Okay, so now whole thing is integration, so the square is outside of the integration, plus 3 times expectation of this gamma. What is this gamma? That is difference of this sigma. Okay, for where this x is with z1 initial, here x is with z2 initial. So whole square, the square is outside the integration. So this part we are doing to establish uniqueness. So here since we are doing uniqueness, so for the time being we assume existence. Okay, so that's why we can write down xz1, xz2 because we are assuming that solution exists. We are just showing that okay, it would be unique. So now we first consider this term integration with ds. So whole square is there. We use Hilbert's inequality. Here we can write down as as 1 times as, so that whole square is less than or equals to a square ds and 1 ds 0 to t, and this part is t, integration 0 to t a square ds is here. Now for this term, here we use Ito's isometry. 0 to t gamma s dws whole square is equal to 0 to t gamma s square, the expression is there. Okay, so gamma s square ds. Okay, so we are using Ito's isometry to get this. So both the places we have obtained integration of some square terms. Okay, the square outside the integrations we could avoid now, which is inside. So we are applying these estimates here at this stage. So this left hand side I have written exactly the same, but right hand side I would change now. So this first term is as it is, 3 times expectation z1 minus z2 whole square. Here for this term we got the t times this a square, where a square is like this difference square, and we have Lipschitz continuity of b on the second variable. So this difference, okay, for Lipschitz continuity coefficient, Lipschitz coefficient d would appear therefore. So this square would be less than or equals to d square times the difference square. Okay, so I would get t times d square of this thing, expectation of xz1s minus xz2s square ds coming from this. However, from here we would have this thing gamma square, where gamma s also involves this sigma difference, and here we again apply the Lipschitz continuity property of sigma on the second variable. So this square of the difference would be less than or equals to d square times again this square term. So from here we are going to get this 1 times here, and from here we are going to get t times this thing. Okay, so these two terms would contribute these two terms. Okay, so 1, 2, 3, so 3 terms we have obtained. Now we observe this map t to vt. What is vt? Vt is defined as expectation of xz1t minus xz2t whole square. This term anyway appeared on the left hand side of the above inequality. So here this term appeared, expectation of xz1t minus xz2t whole square. This term also appears here. So if you take expectation inside, can you do that? Yes, you can do that, because inside term is non-negative. So you can apply Townley's theorem to take it inside. So this expression, this is a function of t, and that same function appears here also, but there is an integration involved here. So if you write down that function as v, which we do now, so vt, then the above thing is vt is less than or equals to f plus a times integration 0 to t vs ds, where f and a are constants which do not depend on time t. So here we write down f is equal to 3 times expectation z1 minus z2 whole square from above, and capital A is 3 times 1 plus capital T d square. I had small t there, but that was depending on small t, but I would like my capital A to be independent of small t, so I replace small t by capital T, since it is less than or equals to sign, so we can do that. Okay, because anyway this is a non-negative quantity, so I can replace by the larger quantity capital T. Okay, so this is precisely the inequality for which Grunwald's inequality can be applied. When we have such a function v which satisfies such type of inequality, then of course f and a are constant. Okay, and then we can obtain that the V which satisfies this inequality would satisfy the type of Vt is less than or equals to capital F times e to the power of a t. Okay. So, we are going to use this conditions here. What we can obtain from here, since it is e to the power a t, so we understand that this is less than or equals to capital F times e to the power of a capital T. So, we obtain that this is finite. Okay. So, it is a bounded function. Okay. So, now next what we do is that if z1 is equal to z2, okay, so then what happens to f? Then f becomes 0, and then V of t is less than or equals to V of t is anyway non-negative because it is expectation square of some random variable, is less than or equals to 0 times e to the power of a t. So, it is 0 here on the right hand side. So, V becomes 0 function. Okay. V becomes identically 0 function. So, what does it imply? That implies that if your initial conditions match, then your solutions would also match. Okay. The probability of x z1 t is equal to x z2 t, you would observe that is, I mean, they are equal with probability 1 for each and every t. Okay. For each and every t, we would see that okay, they are equal. So, next what we want to show, we want to show that okay, they are unique not only in modification sense but in distinguishable sense also. Okay. So, what does it mean? That here we can put this for all t small t belongs to 0 to capital T inside the probability, but it is not clear how. Here what we do is that since it is true, so we can take only set of rational numbers in 0 to capital T. So, then the null set on which this is not obeyed for t in rationals, those are countably many zero measure sets. So, union of that would again be zero measure set. So, complement of that zero measure set would be that probability 1. So, here we write down that x z1 t is equal to x z2 t is equal to 0 for all t rational. Okay, that probability would be 1. We can do that. Now, we use the continuity property because we assume the existence of continuous solution of the SD at this stage. The proof of existence would come later. So, these two are continuous. Since they are continuous and they match, okay, on set of rational numbers, so and rational numbers are dense in real, so we would get that these two would be equal for all t in 0 to capital T. The probability would be 1. So, this ends the uniqueness property of the solution.